Okay, so we just talked about scalar multiplication, which is basically stretching your vector or flipping it and stretching it. And of course, you can also smush the vector too. It's like a dilation of the vector. The dot product is a bit different. The dot product is an idea of multiplying two vectors together. And what you get out after doing this is not actually another vector. This is different from everything else we've talked about. What you get out when you take the dot product is a single number. You get just a number as an answer. So let's define the dot product, and then hopefully you'll see why you get a number instead of another vector. So if u is a vector AB, and v is a vector CD, then we define the dot product as this little dot between the vectors that looks a lot like the multiplication symbol. Then u dot v is equal to AC multiplying the first coordinates and then multiplying the second coordinates and adding those two results together. And if you look at this, this is a number because it's a number times a number plus a number times a number. So the result of this, of the dot product, is not another vector, but instead just a number. So I'm going to write this to be very clear. The result from the dot product is a number. Is a number. Not a vector. Scalar multiplication gives you a vector. Adding two vectors gives you a vector. Subtracting two vectors gives you a vector. Taking the dot product between two vectors just gives you a number. Doesn't give you another vector. Okay? It's very easy to get tripped up by this. So just go back to what is the dot product doing. It says multiply the first coordinates, multiply the second coordinates, add them together. That's the dot product. Okay, let's look at some properties of the dot product now that we've got it. So, some algebraic properties. And this is why I said it behaves, it looks like, it talks like multiplication. It's because it really is a lot like multiplication. Okay, so let's look at some algebraic properties of the dot product. One of the properties that we've got is basically the commutative property, and that's that u dot v is equal to v dot u. I'm not going to prove all of these properties because a couple of them I'll ask you to do, but it should be pretty straightforward to see that the order you do the dot product in doesn't matter. If you do A times C or C times A, you're going to get the same number. And likewise, if you do B times D or D times B, you're going to get the same number. So this is the commutative property. Commutative. Commutative. Just like vector addition was commutative, the dot product is commutative. Another one we've got is that u dot v, plus w, if you dot one vector with the sum of two vectors, that's the same as taking the dot product and then of each vector and then adding the result together. And what does this look a lot like? This u is basically distributing to both of the inner vectors. This is like the distributive property. Now, why would this not make sense? U dot, I'll just write it over here on the side. So why would this not make sense? U dot v dot w. Well, if you think about what the dot product gives you, the result of this is a number. So this is a number. So this is saying u dot, I mean, we can call this number t. U dot t. But we don't have a way to do a dot product with a vector and a scalar. You need two vectors in order to do a dot product. So this doesn't make sense. Therefore, this doesn't make sense. The only way you can do dot product is if you have two vectors. So you need two vectors in order to actually take a dot product. Okay, what's the next property? One is that if you multiply, so let's see, what was it? Okay, so say you have some scalar multiple on a vector, and you dot it with another vector. Then this is the same as u dot t times v. So you can just kind of move this scalar around. And it's also the same as t times u dot v. And this is almost like the associative property. It's like it doesn't really matter what order the multiplication happens in. You can do the scalar multiple on the initial vector, or you can do the scalar multiple on the second vector, or you can do the scalar multiple after you take the dot product. You can just multiply the result. And then the last one is maybe one of the more important ones, is that u dotted with itself, any vector dotted with itself, is equal to the magnitude of that vector squared. So it's the magnitude squared. Okay. So those are a bunch of properties about the dot that involve the dot product. I'll go down a little bit.